Swayam Prabha. Digital India. Educated India.
Okay, good morning. So in this lecture, I'll be talking about design of a continuous fractionator or the distillation column using this method called McCabe-Thiele method. So this McCabe-Thiele method is a relatively easier method to design the distillation column. When I say design, what I mean is that we are looking at what is the number of theoretical plates we need to achieve a given separation. Okay, that's a question that you're trying to answer. Other design problems such as diameter of the column can be obtained based on pressure drop calculations. This particular method involves several assumptions. I will enumerate them as we go along. And I also mentioned in the last class that the entire distillation column can be considered as two parts. One that is above the feed point is called the enriching section, and the one below the feed line is called the exhausting section. Okay, so the design will involve treating these two sections separately and then drawing the operating line for each section. So first we will talk about the enriching section. This is also known as absorption section. So this is the upper part of the distillation column. So you can see that the feed is somewhere here. Okay, feed line is somewhere here, just below. I'm only showing the part above the feed line, and plates are numbered from the top as 1, 2, and all the way up to some small n. The horizontal line that I show here are the plates, which allows contact between the vapor and liquid. And at the top of the column, the vapor goes, and then this goes through the condenser where the vapor is condensed, and then some part of the liquid is sent back as a reflux, and then the remaining is taken out as a distillate. You can also see the notation I'm using. So if you look at the topmost plate, plate number 1, the liquid that is leaving the plate has a composition of X1, and the vapor that is leaving the first plate has a composition of Y1, which is a vapor, and that's what is shown here also. And we will assume that in this particular McCabe-Thiele method, we will assume that the condenser is a total condenser. Condenser is a total condenser. What it means is it removes all the latent heat from the vapor and then converts everything into a liquid. Okay, so that's what this total condenser means. So total condenser means that all the vapor is condensed into a liquid. So both reflux and distillate are liquids at bubble point. So what it actually means is the following. Let's say I have this Txy diagram, P constant, so this is boiling point of B, this is boiling point of A. Okay, so this is a Txy diagram. If you think about this vapor coming at G1 at Y1, it is somewhere here. Okay, so this top curve here is the dew point curve, and the bottom curve is bubble curve. So what's happening at the condenser is that a vapor consisting of the composition Y1 here is cooled, okay, is cooled all the way down here, okay. I already talked about this, that if you cool a vapor, the first thing is you cross this dew point where the first liquid droplet will form, and then if you subsequently cool, you come to some point here where it phase separates into partly vapor, partly liquid, and then if you continue this, at this point when you hit the bubble point, you would have actually condensed all the vapor into a liquid, and in the condenser you basically have the components corresponding to this particular composition as well as the temperature. So both the reflex and the distillate would be corresponding to the bubble point at that particular composition. So in this, Y1, X0 and XD, they are all the same, because I have come from a saturated vapor to all the way to the saturated liquid without changing the composition. So this is what I mean by total condenser. So what would be a partial condenser? A partial condenser would be somewhere where you stop the cooling point here, and then you draw the liquid corresponding to this temperature, and then vapor corresponding to this temperature, but the composition of the vapor and liquid are different here, and this condition is not valid anymore. Okay, so in McCabe-Thiele method, we are going to assume the condenser is a total condenser, so that the reflex and the distillate are all at the bubble point temperature, and the composition Y1, X0, XT, they are all the same. Then we also assume that the stages are ideal. So this means that Xn and Yn, Xn and Yn are the composition of the liquid and vapor leaving nth tray. These are at equilibrium. Also, we will assume that L and G are constant. So if you look at this, the enriching section, there is a mass transfer between the vapor to liquid, okay, and vice versa. Because of this, there will be a minor change in the flow rates of liquid and vapor, but we are going to assume this to be constant, okay. L and G are very constant, so that I can treat each tray almost same with respect to the flow rates. Compositions are changing from one tray to the other, but we will keep the flow rate to be constant, okay. So this is another assumption. So to summarize, in McCabe-Thiele method, the most important assumption that we are making is that the condenser operates under total condensing option, that all the vapor is condensed into a liquid at bubble point, and we are saying that the stages are ideal, so that all the leaving streams at a given tray are at equilibrium, and thirdly, that the flow rates, liquid and vapor flow rates L and G, are held constant, okay. So these are stricter assumptions. Yeah, this won't work for? Yeah, so like I said, these are assumptions we are making. If you want to do more sophisticated calculations, it is there, okay. The other method I was talking about, like punch and Sauerett method, that allows, including all L and G variation along the column, but in this particular method we are going to treat them as constant, okay. So from now on, all we are going to do is we are going to do a mass balance. So let's do a material balance here. So I have drawn a control surface here, and I am trying to write the material balance. Within this loop, whatever is coming in, whatever is going out, that should be satisfied. So that's what material balance all about. So we will write that what is coming in here from the boundary is G, okay. that is a vapor that is coming in, and what is leaving is the liquid from the nth tray and then the distillate. Everything else is within the system. So if you look at from the system and environment point of view, demarked by this envelope, we have to include only streams that are entering from the system and leaving the system. Okay, so as far as this particular control surface is concerned, only there are 3 streams that are coming in and going out together. So G should be equal to L plus D. Okay, G is the total gas flow rate or vapor flow rate entering the system, and L is the liquid that is leaving the system, and D is the distillate that is also leaving the system. Okay, and then we will do a species balance, species A balance. So G times yn plus 1. So you see this G, stream G has a composition of A with a mole fraction yn plus 1. Okay, so G times yn plus 1 will be the number of moles of A entering the system per unit time, and then the number of moles of A that is leaving in L and D would be L times xn plus D times xd, and then we can write yn plus 1 is equal to L by G times xn plus D by G times xd. In the last class I mentioned about a reflex ratio defined as R is equal to L by D, okay, or L naught by D, but we know that L naught, L, they are all the same now. So now I can replace this L with the reflex ratio. So yn plus 1, so L is R times D, and similarly here also I can write L as R times D, so I will say that D times R plus 1. Okay, so we are basically writing the liquid molar flow rate in terms of reflex ratio. So in this equation we are writing L as RD and G as R plus 1 times D xn plus D by D times R plus 1 times xd. So you can cancel the D here. So you get R by R plus 1 xn plus 1 by R plus 1 xd. So this is the operating line for the enriching line. So it has a slope of R by R plus 1, an intercept of xd by R plus 1. So if you want to locate the operating line for the enriching line, the information that you need would be the distillate composition, which is prescribed xd, and the reflex ratio, which is also prescribed because you want to know under what condition you want to operate the column. So if you know the reflex ratio, you know the slope of this operating line, and if you know the distillate composition xd, and you also know the intercept. Okay, so it is shown here that on the x-axis, this is basically the xy equilibrium data. On the y-axis we have the mole fraction of A in the vapor y, and the x-axis we have mole fraction of A in the liquid phase, and the orange curve that you see here, that is the equilibrium line, y versus x, and this is the 45-degree line, and the intercept here for the enriching section is xd by R plus 1. Okay, so this goes from 0 to 1, and then xd by R plus 1 will be close to between this limit 0 to 1. So you can identify this particular point, and you know the slope of this line. The slope of the line is actually, this is wrong, this should be R by R plus 1. Okay, and that is the green line that you see here. So the green line that is drawn with an intercept of xd by R plus 1 and a slope equal to r by r plus 1 is this line, is the operating line. And then you will see also that if I go back here, if I substitute xn is equal to xd, you will see that yn plus 1 becomes equal to xd, okay, meaning that this operating line will touch the 45 degree line at xd, okay, and that is what happens here if you can see. So, the green line touches the 45 degree line at xd, so this is xd. So, in other words, if you want to locate the enriching section operating line, you know xd and find that xd in the 45 degree line, that is one point, and the intercept is xd by r plus 1, and you connect these 2 points, or you basically find the intercept and you know the slope and you can draw the line also. So, either way. So, once we have this what I'm trying to say is that this operating line will actually go through this 45 degree line, and the point of intersection is when xn equal to xd, okay. So, if you extend, suppose if you, let us say you have the intercept and you know the slope and you extend this line, and this line will go through this 45 degree line at xd, okay. So, corresponding to xd you will have y1, because we know y1 and xd are the same, because it is a total condenser, okay. So, that is this point. So, if you look at this, so what we have got is, we have got an equilibrium line and we got an operating line, okay. Once we know this, then we can construct the staircase construction to find the number of theoretical stages for the enriching line alone, okay. So, you start at xd and then you draw this, let me change the color here. So, you start at the 45 degree line corresponding to xd, and then you go horizontally and meet the equilibrium line, and then come vertically down to the green curve operating line, that is stage 1. And then once you reach this operating line and go horizontally, reach the equilibrium line, and then from there you come down all the way to the operating line, that is stage 2. And from this operating line, go horizontally, touch the equilibrium line, and from there you come down, and that is your stage 3, and then you continue all the way to this point, and that would be the number of theoretical stages for the enriching section. The next thing is to look at what is the operating line for the exhausting section, and we will again look at this enriching part, exhausting section of the distillation column, and again do a material balance, get the corresponding operating line. So, you have to think about the feed being just above this tray, mth tray, and from below we are looking at this section called exhausting section, and we are going to do the material balance here. And you can see that this plates are now numbered as m, m plus 1, and all the way up to np. Np is the total number of trays, and since I mentioned that the flow rates are different in the exhausting sections, we associate this overbar for the variables L and G to denote these are the liquid and vapor flow rate in the exhausting sections, L bar and G bar. This is the reboiler where the liquid is vaporized, and we will do the material balance here over this envelope. So, what is the overall material balance for this section? L bar is equal to W plus G bar, right. So, you can see that what is entering this envelope is this liquid, and what is leaving is this vapor flow rate here and also the residue. Okay, this is only the material balance. If I do energy balance, then I have to include the reboiler duty and all that, okay, but here we are doing only material balance. And then you do the same material balance for species A also. Yeah, so we'll draw the envelope like this and then we'll go ahead. Okay. See, this m plus 1 is also some arbitrary number, okay, so it doesn't really matter here for now. So we'll go with this notation, that's what I have in my notes, so I don't want to change it here. But the envelope can be drawn such a way that this fits. Okay. So now what I can do from here, I can write that G bar is nothing but L bar minus W, and I can substitute that here. So this is the operating line for the exhausting section. It has a slope of L bar over L bar minus W, and if you substitute if xm is equal to xw, you will see that ym plus 1 is equal to xw. This point lies in the 45-degree line, meaning that this operating line for the exhausting section will also go through this 45-degree line corresponding to xw. And if you draw that line, you will see that here again we have a xy diagram. In this plot, I have not shown the enriching lines operating line, which we already saw. Okay, here we are looking at only the operating line for the exhausting section. You can see that this operating line touches the 45-degree line corresponding to xw, and this slope will be L bar over L bar minus W. So if I know the flow rates L bar and W, I know what is the slope, and then the green line that you see here would be the operating line. So in this case, what you would do is you would construct the staircase diagram from here, start from the 45-degree line XW, go vertically to meet the equilibrium line, and then go horizontally to meet the operating line, and then you continue this. And this way you will find the total number of theoretical stages for the exhausting section. And you see the first section that you see here actually corresponds to a reboiler, because reboiler is also a stage here. Okay, if you see here in the reboiler, what happens is some liquid is coming with a particular composition, and the reboiler acts like a flash operator, where the outgoing vapor and the liquid are in equilibrium, and this is typical of a flash operation. Okay, in a flash, we take a liquid, we partially vaporize such a way that the outgoing vapor and the liquid are in equilibrium, and the reboiler just do that actually. Okay, so the reboiler is also one of the stage here, and the first stage that you see here corresponds to a reboiler, and from here onwards these are the actual trays. So in this particular analysis, we have dealt with the exhausting section and enriching section separately, okay, assuming that they are above and below the feed line. But feed changes everything with respect to the flow rates of the liquid and the vapor. So it is important to note where the feed line is in this particular operating line. So what we are hoping to do would be now that there are two operating lines, one is enriching and another is exhausting, and they will cut each other at some point of time. Okay, and the slope of these lines are related to the molar flow rates of gas and liquid, and there will be many such intersection points. So the next objective is to find what is this feed line is going to look like and how that interacts with the operating line. Okay, so now I'm going to do a material balance on the feed tray. the tray in which the feed is introduced. Right now we avoided the feed tray, we looked at above and below, but now we look at what is exactly happening at the feed tray and then do a material balance over there. Sorry, what? You're asking why we have not introduced a reboiler ratio for the reboiler. Okay, so that is not needed here because setting the reflex on the top and the reboiler duty will automatically set this. So here the reboiler, as I said, is a flash device. By controlling the heat input, I can change how much vapor I am creating. But in the case of a condenser, I don't have the choice because I am condensing totally. All the liquid is totally condensed. Then I have to know how much to send it back to the column, how much to remove. So there is a control for us to know how much to send. But in the reboiler, we don't have to define a reflex because the reflex is indirectly set by the heat load. Depending upon how much heat you supply, you basically control the flow rate here. So you don't have to separately define a reflex ratio for the reboiler. Now let's look at the feed tray alone, and so this is a feed tray, and what enters to the feed tray is F moles per hour of the feed having composition ZF and enthalpy HF. This feed can be fully liquid, can be completely liquid, or it can be complete vapor, or it can be a mixture of liquid vapor, or it could be superheated vapor, it could be undercooled liquid. Okay, all combination is possible. And then you look at what is coming into this feed. We will say this is L because just above the feed line is the flow rate of the enriching section. We have L. Below that we have L bar. The reason that L changes to L bar is because the feed is now mixed with. And similarly, the gas flow rate above is G and below is G bar. As I said, F can be a mixture of both liquid and vapor. Both L and G can be changed at the feed tray. We will also, so let's say this is Fth tray, just for indexing purpose. We will say the enthalpy here is HL F minus 1, this is HG F minus 1, this would be HL F, this would be HGF F plus 1. So the liquid has a enthalpy of HL F minus 1 and the gas, the vapor has enthalpy of HGF, and below this feed tray the enthalpy of liquid is HLF and the enthalpy of the vapor is HGF plus 1. And before we go further, what we will assume is that in this McCabe-Thiele method, we will assume that the enthalpies are not changing very much. We will say that HGF is same as HG F plus 1 and HLF is same as HL F minus 1. Okay, that means we are saying that the feed is not changing the enthalpy so much, but it changes the flow rates a lot. Okay, again this is an assumption, but in reality there will be some change in the enthalpies also. So we will do a material balance over the feed tray. So if you look at what is coming into the system, feed is coming in, liquid L is coming in, and then G bar is coming in. These are the stream that is coming into the feed tray, and what is leaving the feed tray is G, that is here, and then L bar over here. Okay, so that is a total material balance about the feed tray, and then we also do enthalpy balance. F times HF plus L times HL plus G bar HG is equal to G times HG plus L bar times HL. So, we can rearrange all these things a little bit. So, from this equation 1, we can write that G bar minus G by F is L bar minus L by F minus 1. So, this equation is coming from equation 1, and the reason why we are doing this is because I can substitute for G bar minus G by F in this equation. So, I get L bar minus L by F HL So, I mean what we are trying to do here is the feed, when we introduce the feed, it affects the flow rates, okay, flow rates of the liquid and the vapor, and we are trying to quantify the change in the material flow rates to the enthalpy changes, okay. That is what this equation is. This L bar minus L is the amount of liquid that is added per unit mole of the feed, that should be equal to this enthalpy balance Hg minus Hf by Hg minus Hl, and that we will denote as some letter called Q, okay. This Q is basically the ratios of two enthalpies. The top Hg minus Hf, Hg is the enthalpy of the vapor, Hf is the enthalpy of the feed, okay, and in the denominator you have Hg minus Hl. What do you think would be this Hg minus Hl? What does that signify? So, Hg minus Hl is basically the latent heat, okay, and this latent heat also depends on the temperature. So, this is at a particular feed location. I already said the temperature varies along the column from top to bottom, okay, lowest at the top and highest at the bottom. Feed is somewhere in between, and there will be a corresponding temperature, okay. So, at that temperature you look at what is the enthalpy of the saturated vapor, that is Hg. HL is the saturated liquid's enthalpy. The difference is nothing but the latent heat. That is fixed by, that the Hg, HL, these are fixed by the temperatures here. But whereas this Hf is something that as a user we define, we decide what should be the enthalpy of the feed, okay. For example, if you decide Hf is equal to Hg, okay, you can decide your feed such that its enthalpy is equal to the corresponding saturated vapor enthalpy. So in that case your Q would be what? 0. Or you could say that my HF is equal to the corresponding saturated liquids enthalpy HL. In that case Q would be equal to 1. So Q basically tells you about how much heat is required to heat the feed to the saturated vapor divided by the latent heat. Okay, it's a kind of relative amount of heat that you need to heat the feed to the vapor to the saturated vapor over the latent heat. Okay, so it's a heat ratio, and the Q value can be anything between 0 to 1. And so now that I know the expression for L bar minus L by F equal to Q, and I can also write that G bar minus G by F is equal to Q minus 1, or G bar minus G is equal to F times Q minus 1. So the reason I am writing this is because if I want to know how much amount of vapor flow rate is changed because of the feed, this equation gives me the value. For example, if Q is 1, okay, so that means the feed is saturated liquid, it's not going to change the flow rate of the vapor. So that's why G bar minus G would be 0, that is G bar is G. Let's say Q is 0, so if Q is 0, G bar minus G is just minus F. Okay, so that would be nothing but your feed is entirely vapor, it is only changing the vapor flow rate but not the liquid flow rate. But if Q is between 0 and 1, it will affect both L and G. Okay, and that's something you can obtain from this equation and this equation. To what extent the liquid and vapor flow rates are affected by the feed is given by these set of equations. Alright, I think we'll stop here and then we'll continue in the next class.